And today we are going to develop the stiffness matrix for the truss element, right? So before we did couple of applications using beams, and following are the videos which has been published up to now, and video 5 also has been published for a beam with a UDL, right? If you can I think it's better if you can go through these videos rather than for going for this video, right? So if not, it's okay. So you can send any inquiries to this email, right? If you have. So today I will go through this one, right? So, and yes, first thing is we define the stiffness matrix to bar element, right? You remember the video one. Using the first principles, we define K as E or L -1, -1, and +1, right? So remember this equation, and we define if your bar is like this, let's say this is F1, and the displacement corresponds to that is U1. This is F2, and the displacement corresponds is U2, right? So in that case, you can write F1. That order is very important, right? From where to where you define the bar element, right? So you can write F equals to K times U, right? And right, this is F equals K times U, right? So one can raise a question: if you know the forces, right, can you find the displacement, right? So in that case, you need to multiply this matrix by this inverse, right? K inverse into F equals U. But have a look at that. Does K have a determinant? No, right? Determinant is 0. So we can't find a inverse matrix. Why is that? Right? So something for you to think about. Why you can't find the displacement from this equation, right? It has no solution, right? It has no solution. If you know the displacement, you can find the forces. That's a different story. But if you know the forces, you can't find the displacements, right? Why is that? Something for you to think about. So this will be the exact, so it's axial force, right? So truss element is very similar to this, right? It's almost the same element, bar element. The difference is truss is consist several bar elements connected with each other at even different angles, right? Like this, it's a bar element, this is a bar element, this is a bar element, right? Likewise, several bar elements, right? So within the bar element, we define this is our local coordinate system as well as for this case global coordinate system, right? So if you have something like this, maybe you can draw like this. So if you have one bar element, so this is your global coordinate system as well as the local coordinate system, right? So you define the bar element along its longitudinal axis. But what happens if you have something like this? So similarly, you will define their displacements on longitudinal, right? So what happens is you can't define two global coordinate systems, right? So actually, this is in your XY plane, right? So your global coordinate system is something else, right? It does not change X, Y. So this is a collection of bar elements, right? So some element like this. So always take the element coordinate system from with respect to x-axis. Okay. What angle it makes from the right side of the x-axis. So it will make like this. Not this, okay, not this. Which angle it makes with the positive side of the x, right? Which angle it makes with the positive side of the x. This is making 0, right? So this is making 90, right? This angle. U1, E1. Let's call this U1. Let's call it W1, W2. That notation is very important when you're assembling matrix, right? So this is theta you need, right? This is theta you need. So that means this bar, so these bar elements have now several angles, right? This angle is very critical to define this truss in the global coordinate system. So we need to define a stiffness matrix which is common for each bar element, right? So that means we have to take this angle into account, right? So within this bar element, you only have this one, right? So it is always defined along its longitudinal axis. So this is not going to work in this case because their longitudinal axis no longer remain same for each element, right? This is only for this element. This is the longitudinal axis for this element. So we need to then take the global coordinate system, right? Okay. We will define, so we'll always go in order, right? So we'll take x-axis is first, then y-axis is second, right? So we'll define something like this, an element where this is the local coordinate system for the bar element. Okay, I'll call this u1, this is u2. This is the second node, the first node. Okay, so I call this is the force is F1 and this force is F2, right? So displacement is same as the direction we to define the force, right? In such case, you can write still like this, F1, F2. If your axis is defined on the longitudinal axis, you can write still this into K times U1, U2, right? So in this case, K is this, right? I'll call this K bar element. A-E L. Okay. So I'll define the same element in the global coordinate system. Okay. Same element in the global coordinate system. I'll call this B1. No, I'll call this, sorry, I will make this as W because I have U1 defined in the direction. I'll call this W1 displacement. Okay. W2. In that case, W1, W2. So I have defined the global forces and displacement in global X and Y axis. Okay. So U1, V1, the displacements, right? The same member, right? U2, V2, right? So I'll call this theta. Okay. So you can write W2 and W1. W1 is what? W1 is U2 U1 cos theta plus V1 sin theta. Plus V1 sin theta. Right? W2 is U2 cos theta plus V2 sin theta, right? So you can write this in matrix form. W1, W2 is equal to, so this is going to be cos theta sin theta 0, 0, 0, 0 cos theta and sin theta. This is a 4 by 2 matrix, right? 2 by 4 matrix. Into V1 and, sorry, there are 4 components. I will write this in the next page, otherwise I don't have space. So you can see W1 is U1 cos theta, V1 sin theta. That's no contribution from U2 and V2. So you can write U2 into 0 and V2 into 0, right? So W1 can be written like this and W2. These are displacements. So you can write cos theta. It's the contribution from U1. The contribution from V1 is the contribution from U2 and V2. For W2, there's 0 contribution from U1 and V1, but cos theta from U2 and sine theta from V2. So you have 4 displacements, U1, V1, U2, and V2, right? So this is very important when this is the node FEM output displacement. If you have the FEM output, you can directly convert this into local displacement, right? At the nodes along the longitudinal axis, right? If you know that, you determine this, right? So you know this one as well, okay? So then you can determine the member force. This is for the element, right? The local coordinate system, element coordinate system. So from defined along its longitudinal axis, so you can easily determine the tension or compression, because the nodal output, so whatever you are giving, so let's say this is force is P1 and force is P2 and force is P3 and force is P4, right? So these are according to global coordinate system. That doesn't give you any clue on the tension and compression, but it will have some uh, with the some relationship between with the these forces. I'll show you. So F1. So if you have F1 into cos theta is P1. So this is F1 cos theta. This is F1 sin theta. Likewise, you can write this is F2 cos theta. This is F2 sin theta, right? So from this, you can write an expression. So this is going to be P1, P2, P3, and P4. Right, is equal to, so P1 is only from cos theta, right? So this is anyway related to either F1 or F2. Okay, P1 is directly contributed from F1 and it is cos theta, and sin theta contribution is 0. P2 is F1 sin theta, 0 from F2. This is cos theta, and this is 0 contribution from F1, but contribution from sin theta is actually in matrix form. F1 and F2, right? You can see the same matrix has been transposed here. If you transpose means you swap the rows and columns. You write the whatever the rows as the columns. So first row as the first column, second row as the second column. This is its transpose, right? Okay. So we that's why we call this actually we call this the transformation matrix. If this is T, this is T dash. So the notation we use for the transformation, right? Transpose. This is the transformation matrix. They transform the global coordinates into local coordinates, right? They transform the local forces into global forces, right? So our this step is very critical. Once you take the output from the FEM, you can directly take those into the local displacement and then find the local forces where the tension or compression. That's quite advantage in a truss, right? That's what we are needed, right? So these are the global forces at the nodes, right? Nodal forces, right? So those are related with the tension or compression, right? So here, if you know the global forces, you can go with the sorry. These are the tension or compression, whatever the force on the longitudinal axis, and these are the FEM output, right? But sometimes this will be the actually P1, P2 is let's see in the in example. Otherwise, it's useless. So you can go with. So we know if it is in the global coordinate system, your P1, P2, P2, and P3 and P4 is related to some matrix. This is the global stiffness matrix into uh, U1, V1, U2, and V2. So this is the stiffness matrix for a bar element. Actually, it's a truss element defined on global coordinate system, considering the theta as well, right? Now we need to determine what is this K matrix, right? This is the final form. So we can start it from here, right? I'll call this T dash, okay? I'll call this T dash. So it's P1. So I'll call this P matrix is equal to T dash into F matrix, right? But F matrix you can write as this KB into W matrix, right? This is the stiffness matrix for a bar element or as a truss element uh, along its longitudinal axis. So this is the stiffness matrix we are deriving it for the global system, right? Global coordinate system for any of the member, right? For any of the member. Still, we have to assemble it if you have several members. So if you have several members, you have to assemble it in a way. That's very easy. That's very easy. So you can still go with W matrix, right? The displacement matrix in the longitudinal direction, right? So this matrix W can be written as, so this is actually the transformation matrix into original U matrix, right? Into this is the displacement matrix, right? Actually, This is the U matrix. I'll call this U even if it has U and V component. Okay. So then you can see, so this part is exactly like this. P is equal to some matrix into U matrix, and the remaining is K. And similarly, so you separate P and U, and the remaining is the stiffness matrix you need. So this is the global stiffness. So it's actually the stiffness matrix in global coordinate system for an element. Okay. Element in global coordinate system. Okay. Or else you can say stiffness matrix for truss element, because truss element can be in any angle. It's not like the same as bar element. Bar element, usually in a bar problem, your loads are axial and bars are also connected in axially. But in a truss element, bar element is the fundamental element, but bar elements are connected to each other at nodes in several angles. So in that case, your uh, longitudinal this matrix is not going to work anymore, right? You can't assemble like this because it has some angle. So in that case, you need to consider that angle into the stiffness matrix. So what you're going to do is you define it global coordinate system xy. So that is same for any element. U1 V1 is the U is the x-axis, V is the y-axis, P1 is the force in x direction, P2 is the force in y direction at this node, right? So this is same for alien element. So we take the angle as the angle made with the positive x direction. So this is 0. So always defines in such case. This is the first node and this is the second node. Not this is the first and this is the second. Okay. In that case, that is 180. Okay. Always define the truss elements like this. Okay. Always define the truss element like this. So this is 0. This is making some angle with x-axis, x positive direction. This is x-axis positive direction, right? So you will understand this probably when you are doing an example. So the next thing is, if you simplify this, so you can determine this k element, k truss element is going to be like this. So you have a EOL as well. Okay. Yeah, it's defined as this. Right? EOL. This is not a matrix, so scalar. When you multiply this, you will have this kind of huge matrix into U1, V1, U2, and V2, right? This matrix is going to be like this. I'll show you. I'll write this as CS, sorry, this is C squared okay. So this is also positive. So remembering this is very easy. Remember this portion, this is the part you need. So this part is exactly negative as this, and this part is exactly negative as it is, and this part is similar to this one, right? C is cos theta, right? The element where the element makes with the x-axis positive direction, and S is sin theta. Okay. So this will give you the stiffness matrix for an element in global coordinate defined in global coordinate system. And when we are assembling this, right, that's very important how to do it, right? So let's consider something like this. Right? So this is first node, this is second node, and this is third node, right? So this is the first element. This is the first element, second element, I would say, third element. Okay. So we can define U1 and V1 at this node, and here U2 and V2. Okay. For this node, you can define U3 and V3, right? U3 and V3. And what happens is, finally, you have a matrix. So you can again go with this. So what I was discussing was, truss element is a collection of truss is a collection of bi-elements. So you can't define the same matrix as it is, which was defined for a bi-element along its longitudinal axis. So you need to take the theta into account, right? So here's how you did it, right? So, and you define something like this, and you define the P1, P2, P3, P4 forces. So those are the FEM output, right? into a function of FEM displacement output. So you need to define this K, what is this K matrix, right? So that P is some transformation matrix into F, right? Some transformation matrix into F, and then that that F matrix can be written as KB into W. Where did I get that? So you remember this KB into W matrix. This is KB, right? So right, yes. So this is D dash. This W can be oh sorry, this W can be written again in terms of T into the FEM outputs, right? And you found the FEM output. I'll say this is U matrix, right? This is U matrix. Right? So this is then becoming T dash KB into T, right? So this is something P into U, right? P into U. So this, the remaining thing is this stiffness matrix, right? For an element in global coordinate system, right? When you simplify this, you will obtain something like this as for the element, right? So this C is cos theta, S is sin theta, right? It's pretty easy to remember this because this part is exactly equal to this part, and this part is the negative of this part, and that is equal to this one, right? So outside you have AE over L as a scalar, right? So if you can yeah, it's if I'll discuss with that. So let's consider some example like this, right? For the 60. So it's very important when from where you start defining the nodes. For instance, for the first element, so you define first coordinate as the first node, second coordinate as the second node, first, second, right? Because it's creating then 60 angle with the x uh, positive direction of x, and this is creating positive direction when it is defined from here to here, right? Third node to second node. If from second node to third node, it's not, right? It's a different angle, right? You can take it one, it's 180 was minus 120, but we define it with respect to the positive angle in positive with respect to the positive direction of x. So it's starting from the third node to second node, right? To second element is from third node to second node. That's how we define it. First node, third element is first node to third node, right? First node to third node. This is the element direction, right? This is the element direction which was defined, right? If this was the other way around, it is not 0 degrees. It is 180 degrees with the positive direction of x, right? From this way, it's 0 angles, 0 degrees, 120, and this is 60, right? Then it is easy to calculate, right? So once you define this, so element 1 is from first node to second node, element 2 is third node to second node, element 3 is first node to third node. So once you define this correctly, right, you can go with, so this will be your final output. I would draw this in a different color. So your final entire global stiffness matrix will look like this: P1, P2, blah blah blah, something will be a function of some matrix into U1, U2, U1 V1. This order is very important. U1 V1, U2 V2, U3 V3. This will be a P6, right? So here you have this is the stiffness matrix you need to determine. This is the global stiffness matrix. This is how you assemble. So this stiffness matrix is for a particular element. If you have three elements, you can to determine something like this. This is for the K for element 1. This is K for element 2. This is for element 3. K matrix for element 3, right? This is for each element. You have to assemble this to represent the total truss, right? The whole truss. That's what mean by the global stiffness matrix, and it will have several components. So I will just write these displacement components. So this is not a matrix. This is just to notate the 1v1, u3 v3. This is not just to notate the rows and columns. Okay. So we have a clue on what is this, what will happen to this, and we have to find these forces. Okay. And anyway, we have to impose boundary conditions as well. Let's say this has a pin support. Let's say this has also a pin support. And let's say this node has a load of 10 kilonewton. Okay. So what you need to do is just erase this. Okay. So P1, P2 is the nodal forces at this location, P2, P3, and P4, P6, right? I'll write those as well. P1, P2, P3, P4. Order is very important because always X comes first, then Y comes second, right? This is P5, this is P6, right? Force in vertical direction and force in horizontal direction. Of course, right? So once you go with this, you can determine E1, E2, E3, E4, E5, and P6, right? So first thing is you need to determine this matrix. So make everything 0 first. Everything, okay? So I'm not going to draw each 36 zeros. So keep everything 0. That's easy, right? First, everything 0. Okay, 0, 0, 0, 0, 0. Everything 0. Okay. Everything 0. Write the zeros because it's a waste of time, so I won't write every zeros. So you have to, but you have to. So For instance, if you need to determine what's this element, u1th row, u1th column, right? This element, u1th row, u1th column, this element. So you go to each element, right? And another important thing, so if your AEI over L is same, right, keep it outside, that's okay. But I suggest you, once you determine the element stiffness matrix, this part, you place this AEI into inside, then it's more confident with you, because then you can easily add these matrices, because no scalars at outside. If the scalar is not the same, for instance, this is AEIO L2, this is AEIO L1. So you can't just add these two values. You have to multiply this by this and this by this and then add it. So my advice is to, once you determine these cosine sine these elements, put this AEIO into this side. That means multiply each value from this one and find the matrix. There will be something like this: AEOL into C squared, AEOL into CS. So even your length are same or does not say are not same, that does not going to be a matter then if you add this into inside. So put this into inside, right? Don't keep it outside, right? That's very important uh, when you are assembling the matrix. So you need U1, U1, right? So U1 is in this matrix, but U1 is not in this matrix. U1 is in this matrix. So U1th row, U1th column. So you need this element, and U1th row, U1th column, and you need this element. So make sure you don't have any scalars around. If so, you have to multiply this by AEI over L2 into this element plus AEI over L1 into this element. You have to add those. That's why I told you, once you do this, multiply everything by A over L. Then nothing would be outside. Nothing would be outside once you multiply, right? Then you just need to add this element or whatever, right? So U1 is you need to add these two elements, right? That's U1th row, U1th column, and that is placed here. That has to be placed here. For instance, U2 V3, U2 column, sorry, U2 row V3 column, this element, U2 row V3 column. U2 is not, U2 is in this matrix, but V3 is not here. U2 is not here. U2 is only here, and V3 is also here. U2 column V3. So this element. So whatever you need is, you just take an element, check its row and column, row and the column, right? For instance, this U3 and V3. Check where it appears in these matrices, U3, V3. So U3 is here, V3 is here in the same matrix. You can take this element. This is coming. Check the other things. U3 is here. No, U3 is not here, but and V3 is not also here. And U3 is here and V3 is here. This is coming. Exact row and column should be positioned in one or two or more in more of these matrices. In that case, you have to add those elements and take the final value. That's how you assemble it, right? So assembling is easy. Once you do the assembling, right? So you have to. So sometimes there won't be some cases For instance, in this case, you can't show because 2 is connected to 3 and 1, 3 is connected to 2 and 1 is connected to 2 and 3. There will be some matrix, but there will be some examples where you do not have a proper connection. So now we need to add the boundary condition. We know first node and the third node are pin support. So that means displacements are 0, right? So U1, V1 becomes 0. U3, V3 becomes 0. Right? And U1, V1 becomes 0. And there's, if there's a load, you have to determine. So U2, V2. At U2, V2, you have a load in minus y direction. Second direction, V1 direction, it's minus 10 kilonewtons, right? So in the second direction, you have, it's in minus y direction, that is 10 kilonewton, right? So actually, there are, if you separate the joint, there will be member forces, right? But what can you say? X, Y. So those are all acting at this node, right? But, and you have another 10 kilonewtons as well. So you are considering this whole node, right? Whole node. Then these parts will be cancelled. What's remaining is 10 kilonewtons, right? That's why these are not coming. The remaining force at the node will come, right? So P2 as well, there will be actually a reaction, right? P2, so it's a joint like this. To keep it in equilibrium, that will give some reaction, right, from the supports, right? R1 and R2. From the support, it will give something like this. R3, R4. For instance, if you separate this one, this joint will be like this. There will some X force, Y force, and as well as R1 and R2 from the support, right? No loads acting on this joint. So once you consider this joint, right, these four forces will be cancelled. Whatever remaining is R1 and R2 in X and Y direction, right? So this will be finally R1, this will be R2, this is R3 and R4, right? We will understand this in an example, how to find these reactions. So if it is 0, right, if it's 0, you can close this row, V1 and V1 row column. If it is 0, so close U1 row and U1 column. If it is 0, close U3 row and U3 also, V3 is also 0, and U3 column and V3 column. So whatever remaining can be taken and find the displacement. Then we plug the displacement back and find the forces. These are the FEM outputs, so that we can, because we know the displacements, right? We can plug them in back and find the displacement in longitude along longitudinal axis. And once you do that, you can find the member force, tension or compression. We'll do an example. So if you didn't understand this concept, please go through these videos, right? Video 1 on the introduction, 2, 3, 4. If you have any clarification needed, you can email me, right? It's my email. So please go through this video, link in the description. Okay, link in the description. So thank you.